much for the great introduction. Happy to be here. There is also additional item that is not on the intro, but I am also currently working together with SpaceCoin. So if for those who had a chance, there was a really great talk of Matej an hour ago where he was introducing what we are trying to build. But in today's talk, I'll be mainly focusing on the aspects of trusted execution environments, a little bit provide a general overview on what they are, what the different types of TEs do we have, and what makes them actually interesting from the research perspective, and also try to find a way actually on how to evaluate and use them in the context of blockchain, where we are especially interested in the aspect of a deployment framework that I have been working on together with several of my colleagues. You can see on the paper, and basically try to see how it can nicely fit into the context of blockchain itself. So maybe firstly, a little bit introduce what actually are the interesting use cases we see when it comes to trusted execution environments. Maybe quickly, can you please raise your hands if you have heard about TEs in the past? Okay. I think it's getting better every time, and there is a new word when it comes to introduce to the space. I think TEs themselves are a bit older, but definitely we see more and more discussions about them, especially in the recent months. So this is great. So for some of you already, some of the use cases might be actually familiar. So some of them are very relevant for most of the layer 2 solutions when it comes to the multiple reverse setting, where sometimes it's also being called 2FA, like two-factor authentication, where in general, in addition to your snark proof, you're actually also getting the TE proof itself that can be later on stored on the L1 itself. We also start to see aspects of it when it comes to consensus, so you can actually promote your crash fault tolerance system to BFT tolerance system when it comes to using of TEs. Of course, a lot of current interactions when it comes to AI agents, and we also start to see it in the context of MEV, in the context, for example, of PPS and BuilderNet itself that was introduced rather recently. So definitely we start to see more and more discussions when it comes to TEs, and this talk should kind of a bit try to guide you through the different type of settings when it comes to TEs and what are partially some of the trade-offs they might have. Overall, I think in the current state of TEs as they are, I don't think they are necessarily a silver bullet, but definitely try to provide additional usable approach that can be used in the current systems, and should be also, I think, providing as an additional line of defense, but should not be, as in the current status again, as the main feature that is providing safety and liveness, but rather focusing maybe on some of the liveness guarantees itself. But definitely, I think moving forward, we see a lot of interesting discussions. So there is the initiative called Trustless TEs, or also something that we try to build when it comes to SpaceCoin, where we actually try to provide a very good physical isolation of TEs running on a distributed system on cube satellites themselves. So providing a bit of context, what actually are TEs? So you can think of it like an isolated region on CPU that is providing additional instructions to the users. And the main premise and idea of using TEs is to provide a secure location where you can actually run your code and the data in use. They aim to offer confidentiality and integrity. And also what is very relevant for the blockchain use case is they provide remote attestation capabilities, meaning that you can provide a proof or attestation report that actually others can verify to get a confidence that you are running your sensitive information inside of a TE. The attestation itself is providing a form of aspects when it comes to providing the state of the system. Either it can be the operating system, the binary, and other relevant information that are, of course, later on being signed. So we don't have the time to dive into the detail, but happy to discuss further on actually how does the attestation root of trust basically is issued when it comes to collaboration with various manufacturers. And there's currently quite a lot of ongoing research from my perspective as well when it comes to the comparison between the cloud-based deployments and the attestation report generation, but also bare metals, where of course both of these different settings provide different type of trust assumptions when it comes to the application in blockchain. Very important, I think it is very interesting and good feature is that you can actually provide additional data into the attestation report itself, meaning that actually people can later on when they are running a TE, you can, for example, insert into this custom information a certain type about your private key that basically it's actually running, or your binary is running inside of the TE itself. And again, we don't have to dive into the details, but this type of flow differs from manufacturer to manufacturer, and it's quite an interesting stuff when it comes to actual deployments. Providing a high-level overview, there are two mainly discussed technologies. I will be also talking about some other types of technologies out there. That one of them is the process-based, this is the one on the right, and the VM-based solution. For those of you who have heard about TEs, most likely you have heard about Intel SGX and all of the hacks of Intel SGX. So this is basically the solution on the right, where you are running your VM and only certain components of your binary are basically running inside of the enclave. Whereas the VM-based solution are providing more user-friendly capabilities because you can deploy whole your virtual machine, including the operating system, inside of the trusted compute bounds of the TE itself. Which of course makes it much more easier to deploy and run your application while getting additional confidentiality guarantees and isolation. But of course you have to also consider that the additional amount of information and basically code that you run within the VM is also assumed to be trusted, and it's kind of increasing the TCB itself. Some prominent examples of each of the individual technologies, as I was mentioning, Intel SGX is a very known solution as a process-based solution, but we also see successors of Intel SGX, which is Intel TDX. Then from the AMD family, we have the AMD SEV until the latest version of SMP. We also have some more exotic approaches on the RISC-V CPU architecture, namely the Keystone project. And of course, on ARM, most of us are using different type of flavors of the process-based solution in our phones as a part of the ARM trust zone itself. But there also started to be actually a shift more towards this VM-based solution called confidential computing architecture from ARM that later on different manufacturers and providers can actually implement in slightly their own way. There are also some other types of families that are not belonging to either the process-based or VM-based. Mainly it's the hypervisor-based solution from the AWS Nitro Enclave, and also some part that is like focusing on the software plus physical isolation, where this was already introduced by the co-authors of Space TE, namely by the team from Stanford. That is basically some of the aspects that we are currently working on and trying to enhance. And for those that are interested in the AI and want to run their models locally, you can also have a look on the solutions from NVIDIA, where we start to see TEs on GPUs itself. When it comes to, for example, H100s and H200s, I think Fala is doing a great work when it comes to these deployments that are already available to people. But this basically relies on combination of both TE on the CPU, but also on the GPU itself to deploy your particular solutions themselves. There are also some levels, so this was actually quite a nice differentiation I have seen. So credits to Paradigm, there was a really great event at DEF CON last year in November, and they kind of try to also split the different type of settings into different levels, where I think the overall target would be to provide a cryptographic computer, which of course is something that everyone is aiming for when it comes to programmable cryptography, where you can have heterogeneous open TEs, for example, like the TrustST initiative that is happening there, together with a combination of some additional cryptographic solutions like FHE or MPC that basically is providing and running in this type of setting, which of course the idea is to have as least as trust as possible and try to really mitigate the overall attacks also on the supply chain itself. So we definitely see that there is still quite some work to be done in the upcoming years when it comes to reaching the highest level of confidence and trustlessness itself, but definitely see a lot of interesting initiatives that are being led by players in the space. So it's going to be, I think, very exciting to see how this is going to evolve. Diving back into the more like the state of the art when it comes to that, I was mentioning about Intel SGX and TDX and AMD SEV that are the VM-based examples, and the main, I think, differentiating factor we see is that it's basically the code changes. So with Intel SGX, even though there were frameworks like Remind SGX or others, you still had to actually modify your code, and you as a developer had to really think on how to prevent certain types of attacks when it comes to deployment and interaction with this type of enclave. And you had to make sure that you are actually able to provide and design the system well to identify what are the sensitive information that should be running in there. Nevertheless, the technology is known. It's being still used. We see it actually most when it comes to, for example, most of the multi-prover settings and solutions out there that are being used by most of the L2s are actually relying on Intel SGX, and even Intel TDX internal is actually also relying on Intel SGX itself. And then the aspect of AMD SEV, it's basically fully VM-based solution that is also being developed over the years. So now I have introduced that there are actually quite a lot of variations when it comes to different TEs and how they can actually, how they differ slightly when it comes to the manufacturing and so on. And now what we are interested in actually, how can we use the TEs in the context of blockchain and find a way actually on how to assess these capabilities in a structured way and see how they can be used in combinations with various types of the individual stack of the blockchain stack itself. And of course, when it comes to such type of evolution, we are interested in doing it in a reproducible manner, meaning that if we actually propose a solution, we have a way on how to evaluate it, and others can also verify that our approach is valid. We want to have the option and granular control on how to actually compare these different architecture and understand their implications. And lastly, we want to also have a common ground that currently we are a little bit missing when it comes to the solutions that are out there and how they can be actually developed. So for that, we are looking for the ways actually how to deploy these complex systems in a local control environment. It doesn't have to be only local, can be also, of course, maybe in cloud, and provide the emulation of such type of realistic deployments. So for that, I can provide just like a high-level overview stack of our solution. So of course, for those who are familiar with the blockchain space, we always do most of the activities on the individual layer of the stack itself when it comes to data layer, network layer, consensus layer, execution layer, or the applications, of course. There is quite a lot of ongoing activity as well as a part of my research focusing on the crypto layer when it comes to threshold cryptography. And of course, we are looking for the synergies when it comes to TEs with actually what is the hardware providing itself and how it can be integrated into the applications running above it. So, in order to be able to deploy and evaluate these different type of architectures, we are interested in these local deployments. So either we try to deploy the type of systems in a local fashion, which is mainly building on our previous work that we have done, but we also actually support different cloud deployments. The reason why we support also different cloud deployments is to enhance the capabilities of different type of scenarios, and also as we see more and more applications in the wild actually also rely on the cloud itself. Especially in the distributed computing community, we see that most of the experiments are happening on public infrastructure, such as AWS, Google Cloud, or Microsoft Azure. And for that, of course, we need to make sure that when we want to assess the systems, we should be also having the capabilities of deployments inside of this type of setting. And when it comes to designing the experiments, we are interested in doing it in such a way that is, of course, reflecting the capabilities of the system. So we have to do a lot of theoretical assessments of how such systems can work. So this is, I would say, the most time-consuming part, because you have to know on what you are interested in to identify the right problems and ask the right questions. And later on, you are trying to deploy these type of solutions in practice. Since the systems keep changing and evolving all the time, you of course can consider black box testing, meaning you just take it like a black box solution that you don't necessarily touch, but of course you are also having the combination of white box testing, meaning that you're actually inspecting the code itself and see how it can be fully integrated into the respective flow itself. When it comes to actually analyzing such systems, you are interested in having various capabilities when it comes to collection of different types of metrics and parameters to collect and valuable insights about the whole system itself. An example would be, okay, we want to understand in full form how L2 interacts with L1. For that, we have to deploy the particular L2 solution, meaning, for example, Scroll or Polygon or others, on our own self-hosted layer 1 solution to understand what are the individual bottlenecks and how actually this integration can look like, and see how the integration with other components can actually be achieved as well. And in order to do so, we of course have to spend quite some effort in porting these type of solutions, but eventually it provides us the option to really understand and do a close evaluation of the individual parts of the system itself, or possibly also extend them to get additional type of insights and improve on the stuff that we identify relevant. In order to deploy it, we are usually relying on a management host that is basically providing the orchestration layer that is later on being configured in such a way that we can provide various inputs into the experiments we are setting up. The network itself is later on basically set up the way we want as a system under the test. And lastly, we also provide an output that basically are the individual insights when it comes to running such type of complex system in our local environment. Here, just like a little bit kind of some part of why do we focus on the TEs in the initial phase. I think the discussion here that is something why people are considering it as of now is because it provides reasonable amount of security while also suffering from less penalty cost when it comes to the usage of such system. For that, we have just like two type of experiments briefly because we don't have time to dive into too many other details. These are CPU evaluations where we are actually evaluating a baseline without TE with which is basically running purely on bare metal. Then we have a Docker container solution. Then we have kata containers. It's like a lightweight confidential container itself. And then just like QEMU VMTEs. And when it comes to the evaluation of the impact on the CPU, we basically see that the curves are rather comparable, meaning TEs are also becoming more and more relevant because the overhead they are providing is negligible, in comparison to the security features they offer. And of course, we can dive into more details when it comes to that, but we can see it the same rather holds for also aspects of I/O, but also I/O when it comes to networking, or also the parts of storing data on disk itself. The reason why the performance is comparable is because there is a lot of internal hardware offloading basically and support by the manufacturers, which of course is something very attractive, and it's building basically on top of various types of hardware acceleration that was already developed over the years by the respective manufacturers themselves. Something that I just want to also mention that basically this type of methodology is currently being used in practice as well, and we will be using it for building and evaluating the layer 1 stack. So when it comes to the granular control of the system, we can definitely extend it by various network consideration when we are interested in the mixture of emulation and simulation. And for that, basically, we are willing, or we are having the granular control of introducing different types of latencies and many others. We want to also understand when it comes to, for example, porting EVM to different type of environment, for example, from x86 machines to your Raspberry Pi, what will be a fair cost to calculate on the opcode when it comes to the specific overhead, and provide a robust pipeline that actually others can later on investigate and look into when it comes to arguing what are the type of guarantees the system can provide, both on the security, which will be of course mainly theoretical front, but also on the performance level itself that others can later on verify. So the key takeaways and part of the future work, we definitely envision that TEs themselves are providing very interesting capabilities and can be used in a heterogeneous setups as they are. We definitely see that for that we should find a common ground on how to be able to evaluate them. For that, we have introduced the framework that you can later on also find available online, and also we have an open source implementation of it that can be used that is aimed to provide evaluations of different L1 solutions. And we believe this is like a good stepping stone for kind of setting up the ways on how others can compare and understand the system when it comes to the guarantees and performance it can provide itself. So with that, I would like to thank you, and feel free to reach out. You can also find the links here to me, or also to our blue paper that we have published recently. Thank you very much.
Thank you very much. I think we have a couple of minutes just for the last one question, for a quick question, so please feel free.
Why was there a spike on slide 19?
On the left, you mean?
Yeah.
So we assume that this is due to the caching, basically, because we see that the cache basically is no longer able to handle the particular data set at that given point in time. So this was something that the data set, it's so this is the particular triad benchmark. When it comes to that is basically you can provide it different larger or smaller data sets that basically are just crunching through the computation itself, and you're just specifying on how large the amount of data should be.
Thank you very much. I think we have one more question. We have like 1-2 minutes, so a quick one, please. Did you want to?
Yeah, thank you. So my understanding is that TE is tightly related to a processor itself.
Correct.
So how do you imagine if A had a key and wants to transfer it to B? So a secret key wants to transfer it to B, and you want to make sure that A deleted the key after transferring it. How would you imagine doing this using a TE?
Mm-hmm. So basically the question is if we want to, let's say, migrate our machine to different type of location. I think you would have to implement this type of logic as a part of your application to make sure that this is deleting it. So let's say the TE can provide the guarantees that you are running a particular logic, and you know this is running inside of the TE, and the TE can later on, if it's supposed to do the job correctly and it's not compromised, can execute the logic in such a fashion. So maybe after you forward your key to the other part, and your logic is, let's say, open source, people should assume that you're running the particular binary inside of your TE that is responsible for this type of task. I think this could be one kind of naive solution I can think about on top of my head, but I can imagine there can be some additional works towards that.
There's also a recent paper, conditional recall.
Yeah. Yeah.
Thank you very much, everyone. Thanks a lot. In case you have any questions, reach out to the speaker afterwards.
Yeah.
Thank you very much.
Thank you.